Today, we will be presenting Galaxseavers' design document for the CubeSat challenge.
After our satellite is in position, it will undergo image mode, where within a 60-second interval, it will begin taking a picture every 10 seconds for a total of 6 pictures in that minute interval. We notice that while taking pictures with our camera, it has a 6-second delay every time it takes a picture, which is why we're taking only 6 pictures to factor in for the delay. Whenever the satellite takes a picture, it will record its position, and it will do so in a text file, and it will find the position out using the IMU that we have attached to the satellite. After the image mode process is done, we will move on to process mode, where we will run each image through an OpenCV plastic detection program. If plastics are detected in an image, we will then figure out the location of the plastics within each image relative to the satellite's position and record that in the aforementioned text file. We will also save the images in a successful image directory. If plastics are not detected, we will save those images in a failed image directory. After all the images are processed, we will go into downlink mode, where the satellite will send a message to the ground station user, notifying them that they can secure copy all the images.
So this is our mechanical drawing of the CubeSat. We plan to put the solar panel atop the top acrylic panel of the CubeSat, and the Raspberry Pi will be attached to the bottom of it inside of the cube, hanging upside down. The IMU will also be attached to that same plate, but because we're using a two-dimensional drawing app, the IMU would probably be next to the Pi rather than below it, but that'll depend on our materials when we're actually building it. Power bank will be located at the bottom of the cube on the bottom plate, and the camera will be attached to the same plate, just outside, facing downward, so it can take pictures of the plastics. This is not indicative of our final design because of potential limitations with our given materials, such as the distance from the Pi and the camera is something of concern right now, as well as the distance of the power bank to the Pi. So things may be moved around in our final product.
I will now go over the smart requirements of our project. We have divided our smart requirements into different categories or components. We'll start with power. We decided that the solar panel shall be on the top of the cube in order to collect power. The solar panel shall then transfer power to the power bank, and the power bank shall power the Raspberry Pi. For communication, the Raspberry Pi Bluetooth shall send images to our ground station computer. The Raspberry Pi Bluetooth shall also send location information of the satellite to the ground station computer to tell it where the ocean plastic is. For hardware, the structural component, or the satellite bus, which contains acrylic plates, screws, nuts, and eye brackets, shall serve as the structural support for the rest of our components. This includes the camera, the solar panel, the Raspberry Pi, etc. The structural component shall hold the satellite together and serve as a mounting place. The camera shall be placed on the bottom of the cube in order to most effectively capture the condition of the body of water and gather data about the amount of ocean plastic that is in the ocean. For our IMU, the ADCS, the Attitude Determination and Control System, the IMU shall provide positioning data for the satellite. For imaging, the Raspberry Pi shall take pictures using its camera to detect plastics based on differences in color or when a different color is detected. Our plan is to first, our camera shall initially be able to detect plastics in a plain background with nothing too close to the color of the ocean. Our camera shall then be able to detect plastics that are not similar to the color of a body of water through color contrast and images coming into the frame. And finally, our camera shall then be able to detect plastics with colors similar to that of ocean water. Finally, we have flight software. The Raspberry Pi shall be able to send images of the ocean to the ground station without overloading the communication link budget. And the Raspberry Pi shall be able to provide diagnostic information to the ground station at any time.
Here is our concept of operations. Before pre-launch, the CubeSat is powered off. During pre-launch, it is turned on and a self-test will be conducted to make sure that the camera, battery, and solar panels are working. An ocean setting, most likely consisting of white poster board and colored paper, will be set up, and once the CubeSat passes the self-test, it is ready to be launched. During launch, the IMU will be activated to find orientation, and all subsystems will be running. The CubeSat will be elevated to waist height or around 3 feet. Orbit insertion will then take place as the CubeSat takes one orbit around the room and takes its first picture when the IMU detects plastic. It will take a total of 6 pictures with 10 seconds between each picture. During idle mode, the Raspberry Pi will process all 6 images and determine the percentage of colors in each picture, as well as the ratio of plastic to water in the image. The Pi will then transmit processed images to the ground station via Bluetooth, and these images will automatically be backed up in a repository in GitHub or the Google Drive.
In terms of mass budget, we have 3 main subsystems, namely the structure, power, and payload subsystem. For the structure subsystem, we have components like panels, aluminum corner rails, screws, nuts, standoffs, and brackets. And the total subsystem mass of the structure subsystem after taking contingency into account is 197.9 grams. For the power subsystem, we have battery, and after taking contingency into account, we have 191.4 grams. And for the payload subsystem, we have components like Raspberry Pi, IMU, the camera, the solar panel with USB adapter board, and the FF jumper cables. After taking contingency into account, we have 80.298 grams. In total, our component mass is 434.68 grams, with about 67.32% of mass remaining. After taking contingency into account, we have a total mass of 469.598 grams, with about 64.69% of mass remaining. And our estimated total cost is $199.2.
So, this is our system level block diagram. On the right here is our structure block. This is simply all the structural parts in our parts list and are not connected to any of the other blocks because they simply hold them. Next is the power block with the solar panels and the power bank. The solar panels provide the power bank with power, so there's a connection. Next up is the command. That has the Raspberry Pi microprocessor, which is powered by the power bank and receives and gives information from the Bluetooth and the IMU, which are in the communication block and ADCS block, respectively.
As for the link budget of our system, we got these data from the CubeSat example. And to calculate the EIRP, which is the equivalent isotropic radiated power, we need to add PT and GT, which are the transmit power and the transmit antenna gain. As for the free space path loss, we would use 4 pi times r, which is the distance between the satellite and the ground station. In this case, it's 400 kilometers because in this case, the satellite is directly above the ground station. And then we multiply that number to frequency and divide by the speed of light and then square that number. Then we have the receive power, which is the EIRP minus FSL plus GR. And then we calculate the power noise using the Boltzmann's constant times the temperature of the satellite times the bandwidth. To find the signal to noise ratio, we just take the difference between the receive power that we calculated and the power noise. We do basically the same thing for the downlink system, except we would switch the transmit and the receive power and antenna gain. And we also take the temperature of the ground station instead of the temperature of that satellite for the power noise.
Okay, so we found the image file size, which is pixel depth times pixel height times pixel width, to be 24,245,760 bytes. Now that's a lot of data to transfer, but we can reduce that by using a JPEG compression algorithm to reduce the image to about 1/10 of its original image size. As for the data transfer rate, the ratio it has to the communication bit rate is 1:1. So essentially, the amount of time it takes to transfer one image to the ground station will depend on the communication bit rate. So for example, let's say the communication bit rate is about 4.2 seconds. Therefore, it will take 4.2 seconds to transmit one image file to the ground station.
As plan and integration. For detecting different colors, we can print a picture of the ocean and put pieces of differently colored paper on top of it. For detecting plastics, however, we surround the plastic bin or any other plastic pieces with pictures of the ocean.